Hello, everyone. Thank you for joining us for this particular session. My name is Jatin. I'm a AWS Database Specialist Partner Solution Architect. And as part of my role, I work very closely with SI and ISV partners to help enable them on AWS database services. Now, on a day-to-day conversation with my SI and ISV partners, I get to review a lot of designs with them while they're implementing or they are finding out various opportunities. And I get to hear a lot of discussions about non-functional requirement in database design. So that is what we thought this time, that let's bring forward some of the frequently asked designs by our partners and present it to them. Along with me is my co-presenter Kiran Singh. Kiran, would you like to introduce yourself?
Thank you, Jatin. I'm excited to be here with everyone. My name is Kiran, and I'm a database specialist partner solutions architect at AWS. As Jatin explained, we worked on some of the feedback from last year's session and put together 5 simple yet powerful topics which we commonly hear from partners. We will try to cover the important concepts, and please note that if we don't cover what's on your mind, we will make sure to leave a mechanism to connect with you and help address your design scenarios either offstage or via email. With that, I will let Jatin explain the agenda for today's session.
Thank you, Kiran. As such, the agenda is really straightforward. What it looks like is we'll give a brief overview of what Amazon Aurora is, and then we will dive straight into the design patterns. So when we talk about design patterns, let me give you a little bit of hint what we are going to talk about. We are basically going to focus on non-functional requirements like high availability, cost, pricing, security, scalability, read and write scalability. We'll touch upon migration and we'll talk about data archival use case as well. So I'll kick off this presentation with high availability and what my partners are basically asking those questions and what kind of design reviews we do with them. And then Kiran will come in and talk to you about scalability and security. And then I'll move towards migration and data archival use cases. So with that, let's just get started. So let's get started with what Amazon Aurora really is. Amazon Aurora serves or was put in place for two basic reasons. One thing is a lot of our customers were asking about cost effectiveness and simplicity of open source familiar database systems like MySQL and PostgreSQLs of the world. And at the same time, the speed and availability and the features which high-end commercial databases provide. So Aurora comes in as a two-edged sword to provide both of these simplicity and cost effectiveness of familiar open source databases like MySQL and PostgreSQL, and at the same time, features like serverless, backtrack, global database, and so on, which are available in high-end commercial databases. And that is presented to you at a fraction of price, at a pay-as-you-go pricing model, and in a very familiar RDS platform backbone. So with that, what you get as an end customer is 5 times the performance of native MySQL and 3 times the performance of native PostgreSQL with all these enterprise grade features. Now the session assumes that you're already familiar with Amazon Aurora and database migration service, and we want to deep dive really on some of the architectural concepts that might help you. So for example, if we talk about availability as the first concept, what availability really means is how available the system is for your end customers and for other integrated systems. This is generally measured by the customers and partners in terms of SLA. And you will hear common terms like 4 nines of availability or 99.95% availability and so on. And whenever you hear those terms, it is assumed from the system that there is some kind of automation in there which will help being or which will help the system being self healing and will self restart upon failure and so on, right? But that's not really the question that the partners are really asking. They're not asking how do I configure high availability or even if Aurora does that, because of course Aurora provides these high availability features, right? But the problem statement sometimes really becomes how do I or what's the application behavior with respect to database? Because a lot of time DBAs report their outage and they say the system is configured this way. So what are rest of the layers in the app stack that they can configure to actually make it better or provide more high availability, right? So that's one question. Another question I really get is from a configuration perspective, how are the read replicas in Aurora different from a failover target, or how do I need to choose that? Should I have one replicas or multiple replicas? If I do not have reader traffic, do I still need a read replica? Another question I really get is, what about unplanned downtime? We talk a lot about it. What about the planned outage? For example, what about major version upgrade? What about there are applications rolling out DDL changes or higher version of application and so on. How do I cater to those kind of needs? So we'll try to address some of these questions in the very first design pattern. So to understand how Aurora actually uses the failover target or read replica, let's first understand in a managed RDS environment, how does the failover actually works. And note that I said managed RDS environment. This architecture is not Aurora architecture. This is the managed RDS with EBS backed storage. That is, I'm talking about anything RDS Oracle, RDS SQL Server, RDS MariaDB, RDS MySQL, or RDS PostgreSQL, right? So for example, if you are connected to one of the multi-AZ instances in RDS, you'll be using some kind of a DNS endpoint, or you are given an endpoint to connect, which will always resolve to the primary instance which is available. Now, if you notice in this configuration, the EC2 instance which runs your database RDBMS server software is actually connected to the EBS backend, and behind the scenes we are doing a storage-based replication to replicate the data synchronously to the other side, which is the passive side. But that passive side or the secondary side is not available to you right now. It is just sitting there receiving those changes synchronously, protecting your data and acting as a secondary in case the failover happens, right? So what happens if the primary instance fails? The automation kicks in. For example, the hardware goes bad or the AZ goes down, the automation will kick in and there will be role reversal, and your DNS will fail over to the other side, while behind the scenes will recover the failed secondary instance. And that is how within 1 or 2 minutes, RDS multi-AZ failover will happen at a high level, right? But the point to note here is that the secondary instance is never available for you to serve the read traffic. If you need a read replica instance, you need to create a separate read replica instance, in which case the automation kicks in, takes a EBS snapshot, configures it for you. You can redirect your reads to the read replica instance and so on. Now that's the point here, that the read instance and the failover instance are two separately distinctly defined concepts in RDS. And that is significantly different from how Aurora does it. So let's take a look at how Aurora does it out of the box. So if you go to Aurora and you configure an Aurora cluster, and if you do not choose multi-AZ, what you still get is a multi-AZ distributed storage. It's a log-based storage, which you get, which spans 3 different availability zones, keeps 6 copies of your data. So it's a highly durable, highly available storage, right? So a lot of customers, they think if I get a multi-AZ highly durable storage with one instance, why do I need another failover instance, or why do I even need a multi-AZ option to be clicked on the provisioning time, right? So what will happen here is the reader and writer endpoint, they point there, and if the failover happens, the automation will kick in and it will try to spin up this instance at the same availability zone or different availability zones. So it will work fine, but what happens if you spin up a read replica instance? Now we call it a read replica instance, but the moment you configure a read replica instance, it also acts as a failover target. And in this case, how it is different from having a single instance is that if the primary instance fails now in this case, the automation, what it needs to do is just nominate that read replica instance to be the primary instance. It will ask it to just take up the primary role, and the DNS flip will happen, and you will see your outage is only for 30 to 40 seconds, which is significantly faster than having only a single instance. Now, the confusing point here is that a lot of people think I do not have an application which has a need to point my reads separately, so I do not need a read replica instance. And since it's called a read replica instance, a lot of people don't tend to think of it as a failover instance. So this is one thing you should keep in mind, that always configure at least one read replica instance which is similar size to your production and has the same parameter assigned, or the parameter group is exactly the same as your primary instance is having, to achieve a high availability on the top of out-of-box configuration. Of course, with this, you can have 14 more read replicas, because Aurora gives you 15 read replicas, all attached to the same underlying storage. And you can configure it for your own needs, and Kiran will deep dive into more of this in the scalability section on how to best utilize these. Moving on, another question is about planned downtime. So what happens if there are application upgrades happening and application teams are mostly working with the DevOps guys, and you hear commonly terms about the blue-green deployment where application maintains two different versions and they slowly migrate the data or slowly migrate the traffic from their production application version to the newly released application version, and they dial up the traffic. So a blue-green deployment is very common with CI/CD pipeline, right? So how do we simulate the same behavior at the data layer? This can very easily be done at the data layer, and it carries the same basic concept. So in this case, you have a blue production box and a green box, which is a copy of your production, on which you will actually apply, say, a major version upgrade. You will test out those changes, make it in sync, and roll it out in production by switching the traffic out to that. Now you would be wondering how Aurora achieves that, or what Aurora provides to achieve that. So this magic is done with the help of Aurora Fast Clone utility. Aurora Fast Clone is a utility wherein you can just click button and create a clone, which is a copy of your production environment. And since we use copy on write protocol, it takes just minutes to spin up an entirely new cluster, and you're not even paying for the underlying storage, because the clone storage is actually a pointer pointing to your production instance, right? So all you're paying for is the instance for the newly cloned instance, the EC2 instance, which get spinned up, and whatever changes you are making on top of it gets built as well, right? So using the fast clone concept, basically you can have a green box provisioned in click button. You can test any of your new indexes or schema DDL changes, or apply a major version upgrade on top of it. And then here we are using MySQL native binlog replication, because the point when you create a clone and the point where you are now after testing the changes, there is a time which has lapsed. So you need to catch up on that, on those changes, right? So you use MySQL binlog replication to replicate that data. And once you have made sure that the data is in sync between the blue and the green environment, you can then put the blue production instance in read-only mode and redirect your application queries to the green environment to make it the new blue environment and roll it out in production. This is the high-level concept. There's a blog. If you want to refer to it, I'll leave it in the notes section. Another thing is that application behavior with respect to the outages. Now, normally when the application fails over, the database fails over, the database guys, they report that the database failed over in 32 seconds. For example, this is a snapshot which we took from Aurora, but the application really perceives it in a different way because the cache is not warmed up, right? Coming back to the same slide, the application will still wait for significantly long time because the cache is not warmed. They have to read the data from disk, and this perceive that the performance is not that good. Now, to cater to those kind of things, we have something called Aurora Cluster Cache Management. And what you need to do is just enable this parameter called apgccm enabled equal to on. You have to make sure that the read-only instance is sized the same as your primary instance, and the failover priority is set to 0. And what Aurora will do in this case, it will make sure that your primary instance cache is in sync with your read-only instance cache. So when the role reversal happens, or when the failover happens, like I showed you, it actually, the application, when it connects to the read-only instance, it sees the same warmed up cache as it was in the primary instance. So in a nutshell, the application does not see that same cold read problems as it was seeing before, right? So what it sees is that if failover happens, the same 32 seconds which were perceived by the database or were reported by the database, it perceives it the same way, and you see the same behavior on the application side as well, because it can just start connecting as if it was connecting to your previous primary instance with the warmed up cache. So very important to keep that in mind. Another few things which I want to really run over is with respect to application behavior, there are certain things that you can do. For example, you can aggressively set TCP keep alives to ensure that longer running queries in your applications that are waiting for a server response will be stopped before a read timeout expires in the event of a failure. So keep that in mind, that it should not be that your application queries are just waiting for the failover to signal that the failover has happened. Another thing is that you should set Java DNS caching timeout aggressively to ensure the Aurora read-only endpoint can properly cycle through the read-only nodes on subsequent connection attempts. Another important point to keep in mind. The third thing is you should set the timeout variables used in the JDBC connection string as low as possible. It's recommended that you use separate connection objects for short and long running queries. These are very well documented points, but often we see that these are overlooked. Another point is, and Kiran will cover it more in detail, is that we highly recommend using reader and writer cluster endpoints. Some customers and some partners, they see that there is an instance endpoint and they end up using it. And after failover, because there has been a role reversal, while you wanted to connect to the primary writer instance, you are actually connecting to the reader instance, because it's the instance endpoint which will always point to the same instance no matter what. So highly recommended that you use read and the writer cluster endpoint provided to you. And last but not the least, we are coming out with a JDBC driver for PostgreSQL. It's in preview. It can exploit the best of the capabilities of Aurora failover. So you should take advantage of that. With that, I'll invite Kiran to cover the scalability section, and she will talk to you for a while about scalability and security aspects of the design.
High availability has always been one of the most crucial part of database design to our partners. Thank you, Jatin, for the great explanation on high availability. Moving on, the second pattern we'll be discussing today is scalability. Let's take a second to discuss what scalability is. It is the property of a system to handle a growing amount of work by adding resources to the system. When I talk to our partners, most of them have questions around how Aurora scales storage and how does I/O flow in Aurora. Along with these questions, our partners frequently ask us about the features available for read and write scaling. So, we thought we'll discuss the common problem statements with you. The first concern is to understand how Aurora scales the storage when there is a huge data influx. The second problem is how to offload your secondary read-only workloads from your writer instance to conserve resources for your mission-critical workloads. So let's go ahead and take a look at the base Aurora storage architecture. What happens with Aurora is that we have a distributed architecture. You can see from the picture here that our shared storage volume is spread across 3 availability zones, or what we call AZs. What happens here is basically we separate the storage and the compute layer. So when something happens in the storage layer, it is not going to affect the compute layer, since storage and compute are independent. Aurora is a log-structured distributed system, which means we send log records from the compute layer to the storage layer. Additionally, along with the fact that the storage volume is spread across 3 availability zones, you have 6 copies of data. 2 copies in each AZs to protect against the failure. If you look at the colored boxes here, they represent the data blocks, and you can see that there are 2 copies in each AZ. The third point is each segment is 10 gigabytes. When you spin up a RDS instance, you will have to choose either IO1 or GP2 as storage type. And you would also need to choose the storage size, for example 200 GB or 400 GB. In Aurora, you don't have to do any of these. All you need to choose is the compute, and the storage is automatically segmented by 10 GB logical blocks called protection groups. As the volume of data increases and exceeds the currently allocated storage, Aurora seamlessly expands the volume to meet the demand and adds new protection groups. Aurora continues to scale in this way until it reaches its current limit of 128 terabytes. So you essentially can allow Aurora to do a storage auto-scaling until 128 terabytes. The last point here is, as you may already know, an Aurora cluster can have one primary instance called writer instance, and it can have 15 replicas pointing to the same storage. If you have a traditional read replica, there will be some type of log shipping happening between the primary and the reader, and the secondary will have to apply the logs to get the changes from the primary. But in case of Aurora, the primary instance and all of the reader instance within the cluster will point to the same storage. So I just want to quickly talk about the protection groups that I mentioned. So here I wanted to show you a pictorial view of the protection groups. Each block that you see here is a 10 GB segment, and each protection group consists of 6 10 GB segments organized across 3 ACs with 2 segments in each AC. We are going to discuss about the peer-to-peer gossip protocol mentioned here in the next few slides. So the next major question we get from our partners is, how does Aurora do I/O? So let's jump right into understanding how Aurora does I/O. The pink box you see is my Aurora writer. The incoming queue you see is an in-memory queue. The hot log is a log in the disk to persist the incoming changes. I have a log called A. It comes into the incoming queue and then it has to persist in the hot log. Once the log has been persisted in the disk, Aurora will send an acknowledgement that it received it and a new log comes in. The same process is followed and the 2 log records A and C are persisted in the hot log. After which Aurora will try to organize the log records. Everything is going well until now. But what happens if a log is lost? Aurora would need the missing log to organize the log records and build the data pages. This is where the peer-to-peer gossip protocol will talk to the other storage nodes and bring the missing log record. After which the log records are coalesced and the data pages are created. To have backups, we send the log records to S3. When you do a read request, you always read the pages. And when you do a write, you write a log. Now that we have seen how Aurora scales the storage and how Aurora does I/O, let's move on to the scaling options available in Aurora. When I talk to our partners, they ask me what are the read scaling options that they can implement with Aurora, which translates to how can they elastically scale out beyond the capacity of a single instance for read-heavy workloads. To address this, I would like to start by explaining the type of endpoints that Aurora offers for connection management. In this picture, we see that there is a Aurora storage, and there is something called cluster writer endpoint. When you create an Aurora cluster, you get a cluster writer endpoint, which you can use to connect to the writer to perform the writes. Similarly, if you create a cluster, you can, with readers, a cluster reader endpoint gets created that you can use to connect to the readers. Now, if you have multiple readers like in this case, then if you use the cluster reader endpoint, the connections are routed among the readers in round-robin fashion. Next, there is something called instance endpoints. Every instance in the cluster comes with an instance endpoint. You can use these endpoints to connect to the individual instances in the cluster. The last one is the custom endpoint for Amazon Aurora. Custom endpoints allow you to distribute and load balance workloads across different ways of database instances in your Aurora cluster. For example, let's say you have a writer and 4 readers in your cluster. You have a heavy analytics workload for which you would want to dedicate 2 readers out of those 4 readers. Let's say that your analytics queries does heavy sort operations and hence you need a custom value for workmem parameter. Out of the 4 readers, you can configure 2 readers to use the custom parameter group with modified workmem for better performance of your analytics queries. You can achieve this by using custom endpoints. On the same lines of read scaling, let's take a look at how autoscale reads in Aurora during sudden surge of connections. Aurora's automatic scaling allows the Aurora DB cluster to cope with a sudden increase in the number of connections or workload. When the connection or workload decreases, Aurora autoscaling removes unnecessary Aurora replicas so that you do not pay for unused instances of the database. Let's say that you currently have 1 writer and 1 reader. You are noticing that there is an unpredictable read workload and the reader is being throttled with CPU. In this case, you will see that the read replica is not able to handle the load, which is affecting the performance in turn. This creates read scalability bottlenecks. Using Aurora autoscaling, you can scale out when your cluster consumes 80% of usage, and when CPU utilization goes below 80%, Aurora replicas are terminated. This way, using the replica autoscaling, you can span multiple readers to scale out beyond the capacity of a single instance for read-heavy workloads. Next on the read scaling is global database. Global database is one of the most used features of Aurora. It serves 2 use cases. One is faster disaster recovery, and the second is for enhanced data localization, which is nothing but faster reads based on your location. An Aurora Global Database consists of one primary AWS region where your data is maintained and up to 5 read-only secondary AWS regions. Aurora replicates data to the secondary AWS region with typical latency of under a second. You issue write operations directly to the primary DB instance in the primary AWS region. So let's take a look at this example here. In this diagram, here is a primary application. It has a reader and a writer in North Virginia. And I have a reader in, let's say, Ireland, and another reader in Oregon. If I have users in Ireland who want to read the data with low latency, they can read from the reader in Ireland. Similarly, if there are users in Oregon who wants to read data from the reader, they can use the reader in Oregon to achieve low latency reads. While we are on global database, I would like to talk about the write forwarding feature available with Aurora MySQL. You can reduce the number of endpoints that you need to manage for applications running on your Aurora Global Database by using write forwarding. This feature of Aurora MySQL lets secondary clusters in an Aurora Global Database forward SQL statements that perform write operations to the primary cluster. The primary cluster updates the source and then propagates resulting changes back to all secondary AWS regions. Let's say that I have an application that is connecting to the global primary cluster in Ohio region. This primary global cluster has a secondary global cluster, one in North Virginia, like you see on the screen, and the other in Ireland and Oregon. Now let's say that I have an application in Oregon and this application would like to send writes. In a normal scenario, the writes would be sent to the primary global cluster in the Ohio region. But with write forwarding, the application in Oregon can write the data to secondary cluster in Oregon, and the secondary cluster in turn would forward the write to the primary global cluster in Ohio. This way, you can forward the writes from multiple secondary clusters to the primary cluster. That brings us to the end of discussion on global databases. Now that we have seen the options for read scaling in Aurora, let's talk about write scaling. For write scaling, I would like to discuss about the fast database cloning. Fast database cloning allows us to clone a production database efficiently and quickly. You can use clone for few major use cases. Let's say that I have a database which is of size 10 terabytes and you want to test the schema changes without disturbing the prod database. Or you want to create a non-prod environment of this 10 terabyte prod environment to create an environment for development or testing. In such cases, you do a backup and restore. Now, doing a backup and restore for 10 terabytes of data takes more time to spin up the compute and storage. But if you use clones, you can create a copy of the prod DB much faster. I remember Jatin was mentioning that mentioning about clones earlier. So let me show you why creating a clone is much faster. So let's say that you have an application pointing to the primary instance of the cluster in availability zone 2. Now let's say I have a reporting application and I create a clone for it in AZ3. You can see that I have created a read-write clone. You can also see that there is a clone storage. Now this clone storage is nothing but pointers to the original storage. If I connect my reporting application to the clone, what happens is it basically has a pointer that says go pick the page from the primary storage. If I want to update a page, I will use a copy on write protocol. What I mean by copy on write is before I do any updates, I actually have to copy the primary storage down to my clone and I will update it on the clone storage. Now, if I do an insert on the clone, then it starts writing to the clone storage. If my primary is writing to a page that is being referenced by a clone, we do a copy on write to write the data. This is how clone efficiently is able to handle writes and reads, making the process of clone creation faster. So summarizing the scalability pattern, we saw how storage is scaled and what are the reads and write scalability options that are available with Aurora. Moving on, the next pattern we'll be discussing is security in RDS Aurora. At AWS, cloud security is the highest priority. Since security is a shared responsibility model between AWS and our customers, AWS is responsible for security of the cloud and our customers are responsible for security in the cloud. As database security becomes more and more essential, our partners ask us questions on how to protect data in RDS, which includes questions around access control, data integrity, and encryption. Let's take a look at the frequently shared concerns around security. Problem 1 is how to secure my Aurora DB clusters. When our partners ask me about how to secure the Aurora cluster, I suggest them few fundamental security recommendations. The first thing is to use AWS identity and access management policies to assign permissions that determine who is allowed to manage Aurora resources. Next, I recommend our partners to use security groups to control what IP addresses can connect to the database on a DB cluster. With respect to encryption, for encryption in transit, I suggest our partners to use SSL connections with Aurora clusters. I also suggest our partners to use Amazon Aurora encryption to secure their DB clusters and snapshots at rest. Our partners have been able to secure their Aurora cluster using these security fundamentals. Moving on to the second concern, what are the security features available to manage user access to the database? This is where I would like to explain about Kerberos authentication and RDS proxy coupled with Secrets Manager and IAM. Let's dive right in and discuss about Kerberos. Now, let's take a minute and skim through what Kerberos is. As you may all know, it's a network authentication protocol that uses tickets and symmetric key cryptography to eliminate the need to transmit passwords over the network. Kerberos is a solution to your network security problems. So let's go ahead and look at what are the benefits of Kerberos. The first benefit is, let's say you have hundreds of database instances and thousands of users. Managing the user access can be a great operational challenge. Authentication using Kerberos and Microsoft AD addresses this with the benefits of single sign-on. The second benefit is keeping all your user credentials in the same AD saves you time and effort because you can have a centralized place for storing and managing them for multiple database instances. And the third benefit is, in a traditional environment, password authentication method requires effort from DBAs and users to maintain or remember the credentials. They also have to take effort to maintain the password strength and expiration policies. I would like to show you a high-level representation of how Kerberos works. Client sends a request to authentication server asking for a server access on behalf of the user. Authentication server retrieves the secret key and uses its password as a key to decrypt the request. This is how the user is verified. After more communication between ticket granting server and authentication server, a Kerberos token is issued to the client, which is encrypted. Now the client sends a request to the server with encrypted Kerberos token, and then the server allows access to the requested resource to the client for a certain period of time specified in the token. So now that we have seen how Kerberos works, this brings us to the end of discussion on Kerberos. The next feature we'll be discussing is RDS proxy along with Secrets Manager and IAM. So, a brief introduction on proxy. Amazon RDS proxy is a fully managed, highly available database proxy for RDS that makes applications more scalable, resilient, and secure. Now, let's look at this representation of how RDS proxy works. On the left side of the screen, you are seeing sample applications like PHP, Ruby on Rails, or you may be running Lambda-based serverless applications. On the right side of the screen, you are seeing your database running on RDS or Aurora. Between these two is the RDS proxy. Now, the applications on the left will connect to the proxy, which sits in between the application and the database. Now, let's discuss how can we integrate other AWS services with RDS proxy to get better security control. So, the usual way of connection in this scenario is you connect to the RDS proxy and establish connections with your MySQL or Postgres database using username and password. On the other hand, what you can do is you can store your secrets in the secret manager, and when you are authenticated with RDS proxy, it will then go to the secrets manager, fetch those credentials, and connect to the database of your choice. Here, we are not storing the credentials in your application. Instead, proxy will connect to the database using the secret that it retrieved from the secrets manager. Since credentials are not stored in applications, this is a great benefit. Another added layer of control that you can achieve with RDS proxy is maybe you don't want to pass the usernames and password to connect to the proxy, but you might want to use the IAM role instead. You can use the IAM execution role associated with your Lambda function or your EC2 instance and use that to authenticate with a RDS proxy. Now that we know how can we use proxy, secrets manager and IAM together, I would like to show you the flow of how the authentication works like. The first step is you request an authentication token from IAM. Here, instead of your password, you get an authentication token back. Once you get this token, You use the token instead of the password to connect to RDS proxy. The next step would be RDS proxy will retrieve secrets from the secrets manager and connect to the database. In this case, because we are using the IAM authentication in our code to generate token, the source code is very secure. You will no longer have access to the password because you are not specifying the password in the configuration file, nor are you hard coding the password in the code, nor are you retrieving the password in the application. There is just no access to password anywhere. So with IAM and Secrets Manager, RDS proxy provides great application security. Summarizing the security concerns, we saw how Kerberos provides network security and how proxy can be used with other AWS services for improved application security. With that, I request Jatin to talk about the next pattern, migration.
All right. Thank you, Kiran. That was an excellent explanation on scalability and security aspect. From here, I'll just like to switch gear because a lot of time partners, when they are talking about databases on cloud, they're also tightly integrated with the migration service. And I'm going to talk a little bit about database migration service, which is actually helpful because it supports so many different source and target endpoints, including relational and non-relational endpoints. And a lot of questions we get to ask about is really about task design, right? So that's one of the use case or the design pattern I really want to cover in this section. So the problem statement which I get to hear from my partners is that they're dealing with heterogeneous migration of a critical application. Of course, they want low downtime because these are production applications, or they have large volume of changes, so they cannot tolerate a longer outage. Sometimes they have large amount of small tables or small amount of large tables, and since they are dealing with migration at a logical level, it's a logical data migration. They really want to be intelligent about database migration service, which we are assuming is the primary tool that we are using for this problem statement that I'm discussing here, right? There are some general guiding principles around database migration service. We are not covering the what is database migration service in this section. There are a lot of other helpful resources which you can cover that. Since this is a deep dive session, I really want to talk about the task design within database migration service because we are assuming that you're already familiar with the basic architecture of database migration service and Amazon Aurora. So general guiding principles around database migration service are that the DMS replication instance, which has the replication software built in, has to be appropriately sized. Now there are T family, M families, and C families, which offer various amount of sizing options for you. So it's very important to pick the right sizing based on your DML changes and the volume of data and so on. Of course, the source, target, and network need to be another important consideration, that if your source or target are under a lot of resource pressure or your network pipe is small, then of course you cannot replicate those changes as efficiently as you would like to. But in this section, I really want to focus on logical task design, on how you can take advantage of one particular design pattern which is generally overlooked or which is generally asked a lot by our partners, which is around how do I load or how do I work with one particularly large outlier table, which is an annoyance because my task is grinding for days now sometimes, right? So for this particular example, we have assumed that there is one large table with 8 million records in it. Instead of 8 million, you can have 80 million or 8 billion. 8 million is not particularly large, but just for the sake of explanation, I've picked up 8 million. And this table I've assumed has a structure which has monotonically increasing order IDs from 1 to 8 million. So what DMS does when you try to do full load or CDC is that for full load specifically, DMS initially will spin up or use 8 different tasks to load the data in parallel, and one task will be assigned to one table. Now, if one particular table is an outlier and is particularly large, you do not want one task to be running and grinding individually for that particularly large table. So what you can basically do is tell that task or divide that task into many different tasks. So for in this example, if I choose order ID and use a feature in DMS for the row filtration, I can say My task number 1 goes in there and puts a filter on order ID and picks rows number 1 to 1 million, and task number 2 picks 1 million 1 to 2 million, and so on, and thus divide it into various different chunks where each task can work in parallel now to load data from the chunks in this table. So rather than having one task grind through a very large table, I can basically divide my table into several different chunks and load it in parallel. This sounds simplistic, but a lot of partners, they make this mistake where they'll just use DMS task definition out of the box, and they'll just assign a task and logically group a bunch of tables, and they'll just let it grind, and then they complain about DMS not being able to catch up. They have done the due diligence which was shared with them, but they have not logically divided the table into smaller chunks, which they can easily do. Now you might be wondering that it's easier said than done, that there is a monotonically increasing order ID, and it's not always the case. There might be complex cases, or my table might be partitioned. Can I take advantage of a partitioning scheme which already exists in the table? Yes, you can do that. DMS provides that facility. And in this example, I'm just showing you a sales table in HR schema, which is laid out with partitions catering to each individual territory. For example, there are partition named P1, P2, P3, P4, which caters to north, south, east, and west region, and data corresponds to those regions. So what I can do in task definition from DMS perspective is that if you pay attention here, it's saying table settings, object locator is pointing to HR schema and sales table in there, and the parallel load section really says partition auto. What it will do is we are just telling DMS to rely on the partitioning scheme which is already there in the database. And if you see in the logs here, DMS will auto assign one task to each of these partitions to load them in parallel. So that's a pretty straightforward way to actually pick that. But what happens if there is a non-partition table and partitions are not clearly defined, or you're not able to pick a key to filter, as I showed you in the previous slide? In case of a non-partition table, we provide you another facility in DMS, which is called range-based partition or boundaries-based partition. Basically, what you can do is you can logically divide your data into various boundaries. How it works is that in this case, I've taken, if you look at the parallel load section, which I've highlighted, there are columns named sales number and region, where I've tried to define boundaries based on some arbitrary sales number and region information in there. So for example, when I tell DMS task to look at this one large table which has sales number and region data in there, it will go in there and will look at the first condition which says sales number less than 1000 and belong to region north, and will pick up all records in that task, right? For the second subdivision, it will look at something which is between 1000 and 3000, sales numbers which are between 1000 and 3000. It will look at region east, and then it will use a third partition, or the third task will be assigned to those where there is no overlap, like the data which was not covered in part 1 and part 2 will all trickle down into part 3. So that way I'm dividing my data in a single table logically into several by using some virtual boundaries into 3 different groups. Now this is just an example, and you might want to be more intelligent to equally divide that data into many different sections by using more than 2 columns. You can use 3 or 4 columns and so on. The whole idea is that you look at your table size, the number of rows, and be able to find some way to actually define some vertical boundaries or virtual boundaries to divide that data into subtasks and let DMS load that individually rather than grinding singularly with one-threaded fashion through that. So very simple but very powerful design, which we really wanted to share with you, comes up more often than other designs. Now moving on to another design pattern, I really want to talk to you about this last pattern for today, which is about long-term data retention. Now, like I said at the start of presentation, a lot of time when people are migrating their applications from, say, legacy databases to open source databases, one thing is, how do I get the same functionality? But more often than not, there are a lot of discussions about non-functional requirement. And this case comes up a lot in healthcare industry or in financial industry, where they say, hey, we have a case where we want to retain our data for 7 years, 10 years, or 15 years because it's a compliance need, right? And when we ask them how you have implemented that design as of today in the existing architecture and on-premises, the answer mostly I get is that they do not purge their data, they just keep it there and the database just keeps growing on. So we can just refer it anytime. Or the answer I get is that they take backups. They take, if it's Oracle, they take, say, RMAN backups. It goes onto tapes, and they have a third party which manages tapes for them. So it goes to long-term storage, and they retain it. But how do they cater to the need of long-term compliance? How do they restore that data? What happens in case of corruption? What's the time and speed to restore? Now that's the question that they file a ticket and those tapes are brought back and they mount that and they restore that. So it's not an easy process, right? Or they have an outdated software version. How do they manage that? If they took this backups on, say, PostgreSQL 10, and now you're running version 15 after, let's say, 3 or 4 years, how would you restore that data? Because now you're outdated, right? Either you maintain those libraries, your binaries in there, or you upgrade it on a more frequent basis. Another thing is, how do you take care of the corrupted media? For example, if those tapes are shipped back to you and you try and restore it, what happens if the media is corrupted? How do you test that? And there is no easy way or no easy answer to that. Another problem with this design is also, how do you cater to the large volume of data? There is no selective way. If your database is now growing from terabytes to hundreds of terabytes, you will keep on backing up every day and your tape volume will be ever increasing and you will always be just dumping that data over and over again, right? So with modern cloud-based architecture, there are techniques you can use, or you can implement certain design to ease the burden of this. I'll show you one example. Before we go there, let's say how Amazon Aurora takes backup. So Amazon Aurora uses a continuous backup or a streaming backup to S3 for the log, because it writes log records and those log records are streamed directly to S3, and that's the way it takes backups, right? But apart from that, we also take a snapshot, periodic snapshot, and you can take manual snapshots as well. Those manual snapshots are actually stored in AWS controlled S3 bucket, which I'm showing here. Now it's AWS controlled S3 bucket, so you cannot download those snapshot. But what you can do is, there's a functionality now which we call snapshot export to S3, and you can basically spin up an export job with which you can actually define that which tables or which schemas out of those snapshot you want to export out, and the export job will run and will dump that data into your user controlled S3 bucket in a compressed industry standard Parquet or open Parquet format, which is a columnar storage format. If you're not aware with that, can be easily used, right? And with that, because it is on user controlled S3 bucket, you can also define a lifecycle policy on top of it to send that data to a cold storage like Glacier. The advantage of this is that, think about time and speed to restore. It's click button, it's pay as you go, it's on demand API available to you all the time. You're not at the mercy of a vendor to just ship you back the tape. So it's available all the time for you to test. There's no software version issues because now you're not keeping the snapshots or keeping the tape mechanism. Some people think of implementing this design by just retaining the snapshot, in which case, again, they'll have to upgrade the snapshot or they have to pay a lot for that storage. But in this case, you are just avoiding that issue. You're not having any software version issues because now you're in an open format, which is just stored on S3, right? And then there is no, there's very high durability. There's no corrupted media. You have S3 assurance of 11 nines. And then it's easy to test as well. Once in a while, you can set up a policy to just restore that data and test it out for you. And then you can be very highly selective with this, and you do not need to always back up your terabytes of data. So for example, if there's only one schema which has this compliance need to back up only those 1 or 2 or 3 tables, you can be very selective about that. Note that this design is generally implemented for analytic use case, where people just use this to do a snapshot export and integrate it with their ETL jobs. But if you think this is a very viable design approach to implement a data archival and data compliance use case as well. In terms of restore, it's really very easy. Since it's a Parquet format, you can directly ingest it to Amazon S3 or Amazon Redshift, for example. You can convert Parquet to CSV. CSV can be loaded to say an open MySQL or PostgreSQL. PostgreSQL, you use copy command to restore it, or you can use a CSV editor to do stuff on it as well. As of today, this functionality is supported on RDS for MariaDB, MySQL, and PostgreSQL, and Amazon Aurora with PostgreSQL compatibility. With that, we are really towards the end of our session today, and there are two key takeaways which I want you from this session. One thing is objectively define your non-functional requirement and use solution architecture to address them upfront. Now, there are many other designs which we cater to. Due to time availability, we cannot discuss hundreds of design with you, but these are frequently asked designs. But the main takeaway here is that put some objectivity into what are the non-functional requirement, put some numbers around that, and try and see how modern architecture can solve that, right? Define the modernization for your customer as a partner. It's very important to understand that cloud-based architecture can solve some of the archaic design issues which were implemented 15-20 years back. With the rapid pace of feature releases, it's not easy to catch up. But if you understand what modernization means for your customer, you can definitely provide a lot more value. With that, we are at the end of this presentation. Thank you. Hope you enjoyed this session.